Hey guys, welcome back. Thank you guys for taking the quiz for me yesterday. So still working on grading those, but hopefully I'll have them done by today. So we're moving on to our last chapter for this unit, which is chapter 5 over the over bell curves and standard deviation as a measurement of what is normal. And so anyway, we're going to start out with 2004 Olympic women's heptathalon, which is 7 different events that they compete against. You can see all the events listed on the left there. So yeah, long jump, high jump, shot put, javelin, all those things. So what's tricky about this is that these women, they compete in 7 different events, but these events, they're all scored differently, right? So some of them, you got like length, or amount of time, and so some, shorter times are obviously better, right? Some of them, long jump, it's in length, so it's in meters, and so a longer meters is better in long jump. So how do you compare time in hurdles to a distance that somebody runs in a long jump? You don't just add all the numbers together. They have different units. You can't do that. So how do you get some overall score for all these different events, and how would you make sure that one event wasn't weighted more than another event or something like that? So really kind of interesting. How would you score a heptathlon between these women that are competing in 7 different events with different units and different outcomes, and how do you add all that together when you have different units? And when some are obviously much longer or shorter than others, and sometimes longer is good, sometimes shorter is better, so it's kind of crazy. So the answer to that question is actually using normal distributions, bell curves, and z-scores, which is exactly what we're going to get into today, and talk about, of course, a little bit of shifting and scaling as well, because that's actually what we're doing when we do z-scores, and it's what allows us to compare kind of apples to oranges when it's not necessarily the same thing and put it all together. So anyway, the 2 ladies who won silver and gold are Carolina Kloof from Sweden and Astra Skuljetti, I think is how you pronounce her last name, from Lithuania. All right, so just to note, she looks like somebody who might break me in half. Anyway, so yeah, kind of like, I think her first name should probably be Helga. All right, anyway, so Sweden and Lithuania, there they are on the map, both Scandinavian countries. That's why they look like they're sisters. Probably. They're probably related. Look like Vikings to me. Anyway, so apparently Lithuania and Sweden, they share electricity. So they have this substation for Lithuania, and then over here in Sweden and under the Baltic Sea, they have the land cable and optic fiber cable. So anyway, they share more than just their gene pool, also electricity apparently. So anyway, moving on, what we're talking about today is Gaussian curve, or a bell curve, or a normal distribution, or a normal curve. It goes by many different names because it's really important, and it came from Gauss. So Carl Friedrich Gauss is probably, he knows as the Prince of Mathematics, one of the most probably best mathematicians of all time. You can probably fairly say that. Was brilliant guy. Didn't get along with people very well because he kind of told them they were stupid. Anyway, so. Anyway, I really liked Gauss. I think he would be pretty cool to hang out with. If I could hang out with a mathematician, Gauss might be the guy for me. Anyway, so goes by lots of different names, but essentially it looks like this. This is a normal distribution here. A few things I want to point out about the bell curve, or a model, which is what we're using, is this point right here is called the inflection point. Now, let me change the color. So inflection points, there we go. So inflection point is when it stops decelerating and starts accelerating. So we're going from a negative second derivative, right, to a positive second derivative. So it's also known as the inflection point. If you are familiar with calculus, I know some of you are, or you're in Calc 1 right now. If you've already taken Calc 1, you know what an inflection point is. But if you're in Calc 1 now, you're doing limits and continuity, but eventually you will get into this and you'll understand it better. So we also have the same one over here. Visually, you just need to be able to find that point, right? So when it stops decelerating, it starts accelerating again. That's going to be this point right here and this point right here. Now, what's important about those inflection points is the distance between the center, which is our mean, and the inflection point is going to be our standard deviation. And yes, that's like a weird 6, but it's a lowercase sigma from the Greek alphabet. So anyway, that is our standard deviation, and where it's centered at is going to be our mu, which is our mean. So the parameters for a bell curve is going to be the mu, or the mean, and the sigma, which is the standard deviation. And that's how we describe, kind of like an ordered pair. You know, we do ordered pairs for x and y's, right? It's kind of like an ordered pair, but for the normal model, we put a little in front of it, saying these are the parameters, the kind of like coordinates or whatever, but which is how we do with the anyway with the Cartesian plane. But over here with the bell curve, our two parameters are the mean, which is what the model is centered at, the average, and the standard deviation, which tells us the distance to the inflection point, which is also very important. So with those two, we can parameterize our bell curve. Now, one thing I want to tell you is that the difference is that the bell curve, which is shown in black here, is a model, okay, where the distribution itself, the histogram, is the actual raw data. So the data gives us the distribution, which is the histogram in green, but the model is used as just that, a model. So instead of working with the actual data itself, we use the data to find the parameters of the mean and standard deviation. And if it is unimodal and symmetric, like this one is, with no crazy outliers that would skew our mean and make it much larger than it should be, and also skew the mean towards the outliers, then we're allowed to fit it with a normal model. Now, models are ideal, okay? So they're not perfect. They don't fit the distribution perfectly, but they're more powerful because they we know how they behave, and we know that all the models can be used to interact with other models as well. So anyway, we prefer to use a bell curve model if we can, if the data itself is unimodal and symmetric. So we always graph out the raw data, the distribution itself in green, the histogram. Make sure that verify that it's unimodal and it's symmetric and it doesn't have any crazy outliers that would skew our mean and increase our standard deviation by giving us some really large deviation. Excuse me. So another thing is that bell bottoms. So, you know, those things that my dad wore when he wooed my mom. I don't know. Those are bell bottoms. I'm sure they have. I think I've seen some people. They'll come back. They'll be popular again sometime. Anyway, so bell curve, bell shaped. Also T-bell, Taco Bell, you know, Live Mas, that whole thing. Also a bell-shaped curve. Okay. Moving on. So there are many different bell-shaped curves. In fact, the normal model is really a family of models parameterized by the mean and the standard deviation. So you can stretch, basically you can stretch out a longer standard deviation or a skinnier standard deviation to fit any model, to fit any data. So here you see the one with the standard deviation of 1 fits the best. Standard deviation of 2 would be too stretched out. Standard deviation of 0.5 here would be too narrow, right? So you can custom fit any unimodal and symmetric distribution with a model, but normally we don't show. Normally, that's also known as a normal model. Anyway, so normally we don't show it. We don't show them when they're really skinny or they're really wide. We just change our X scale. So we can change this X scale. Instead of going by 2s, we'll go by an X scale of 1 or by 1/2 or something. So typically the one in the middle, the one that looks aesthetically pleasing, is the model you'll always see. So something that looks like this. We'll never show a normal model that looks skinny like that. Instead, what we would do is we would just change the X scale in order to make it fit something like this. So we just custom fit it so that we have that value there. Anyway, so this is a normal model. It's parameterized by Greek mu and sigma, which is how you'd spell or pronounce it. I would say mu and sigma, which is just the Greek letters. When we get the actual statistics, which is the standard deviation and the mean, we use the x bar and the s sub x in our calculator. The Latin words come from the statistics, where the Greek words come from the parameters. So the parameters are like the ideal model, and then the statistics are the actual values that we get from our data, like the average of our heights or something like that, and the standard deviation of the heights or something. Okay, so anyway, a family of models, the normal. The other thing is we cannot use the normal model when we have skewed data, whether it's skewed to the left or the right. The normal model will not be appropriate because the mean is going to be too far over compared to where it should be with the actual median or the mode in this case. So it only works when it's unimodal and symmetric with no outliers. If we do have outliers, that outlier is going to increase the standard deviation because the deviation for that one value or a few values are going to be way higher than the rest of them, which would make our model too wide and wouldn't fit our data very well. Also, we can't do it when we have gaps or if it's bimodal or multimodal or anything like that. Like this one would be bimodal, clearly. So it only works when it's unimodal and symmetric. Then we can use a normal model to approximate the data. So here we have the 2 athletes and 2 different of their events out of the 7. We have the long jump and the shot put. So for the long jump and the shot put, both of these higher numbers are better. So at least that we have that going for us. So we have Carolina Klute from Sweden and Oster Schuljek, I don't know how to pronounce her name, from Lithuania. And we can see the 2 different things going on here, right? So like a histogram, we can see the shape of the distribution, okay? But the stem and leaf plot, unlike the histogram, shows us the actual data points themselves, which is nice. So we can see where Ostra showed in long jump. So she had a pretty impressive long jump, but not nearly as impressive as Carolina from Sweden. She looks like she could jump really far. More like break me in half or javelin throw, like throw me. Anyway, I'm picturing the principal from Matilda. That's who she reminds me of. Didn't she like throw a kid or something? And the chocolate cake, anyway, whatever. Such a weird movie. Anyway, same thing with over here on the shot put, but now the roles are reversed. Now Ostra was much more impressive. There's a lot of space between her shot put and anyone else's. She threw that thing really, really far. But Carolina was the second best one. So the question is, who had the most impressive overall score between these 2? So in this one, Carolina was the best, and Ostra was kind of, more than middle of the pack, but you get it. And then this is 1 and 2, but hers was way out there by itself. No one else was close. Also, look at the overall shapes of the distributions. Notice that we were able to fit it with a bell curve fairly well. I mean, there are some gaps in it, some places where it's over. Same thing over here. And we could shift these left and right, but essentially it's about the same, kind of lined them up. So what we're actually going to use to be able to compare these athletes is something called a z-score. So a z-score tells us how many standard deviations above the mean or below the mean, if it was a negative z-score, is the actual data point or the observation. So we're going to find the z-score for how many standard deviations, and if we go over 1 to the inflection point, that's 1 standard deviation. The second one would be 2 standard deviations, so a z-score of 2. And so we can find out exactly how many standard deviations she was. So she was about 2.5, and this was about, I don't know, 0.8 or something. But over here we had like 1.2, and then here we had almost 3. So 3 is obviously more impressive than that one, etc., etc. Then we'll add our z-scores together to see who was a better overall athlete, and that's exactly how they scored these. So first thing I did is I actually put this data into my list. So you don't have to do it. I did it for you because it's kind of annoying. But this is our data from the shot put. It was the one on the left. Let me see. Okay, that's kind of annoying. It was long jump. So this is the long jump data. Oops, spoilers. So long jump data, put that in there, and then I'm going to go to second, y equals, stat plot, okay, good. And then I'm going to go to zoom and 9. All right, so that's the exact same graph here. I just kind of pulled it from here to there. That's awesome. Didn't know you could do that. So if we look at the histogram, first thing, we can, we got a model, we can try to fit it with our model as good as we can, but just looking at that histogram there, is it unimodal and is it symmetric? So looking at it, sure, it is unimodal, but it doesn't really look symmetric because it looks like we got a tail going to the right. So it's not necessarily appropriate to use a normal distribution. Oh no, but if we look a little bit closer in the data, and by closer I mean a little bit more precise, if we change our window, let's go to 70, and we're going to go by a scale of 1.5 instead of 1.8. So our X scale went from 1.8 to 1.5. And then I'm going to hit graph. And now notice that's the exact same data that we graphed, but instead of having really wide bin sizes where a lot of things can kind of be shifted around and it's just kind of loose, now we're going to have really narrow bin sizes so we can see more precisely what's going on here. So whenever we look at this with an X scale of 1.5, all of a sudden it looks much more Yeah, let me move this down here. It looks much more, yeah, it looks much more symmetrical, right? Now there's still parts over here that are a gap that we don't have, on the other side, right? So it doesn't fit it exact, and that's okay. It's just now it looks more symmetrical, and it's still unimodal. And of course, our mode is actually in the center instead of over here. It was kind of off on the left. So that's really the difference we see. So kind of a good lesson to be learned, that by changing our X scale, we can see more precisely what's going on. So we'll make sure that even though the default zoom stat one was 1.8, when we change it to 1.5, it makes it easier to like read the graph too, but also kind of showed us where that data was actually bunched up, instead of having some high-end stuff that was put here and low-end stuff here that was put, and where it made this category look a lot bigger than it actually was. So anyway, kind of cool stuff going on there. So that model can be used. It went from here, now it fits it much more appropriately. The other thing, I think, no, that's pretty much what I wanted to show you there. All right, so a z-score is calculated. It's basically how many standard deviations above or below the mean. You take the observation, which is our statistic, so however far they threw or whatever it was, minus the mean, which is the average for all the girls for that event, like the long jump. Then you divide it by the standard deviation of that. So we're going to take our observation for Kluft, which is 6.78. We're going to subtract that from the mean, which the mean for all contestants was 6.16, and then we're going to divide it by the standard deviation, which was for all 26, which was 0.23. So let me go ahead and show you how I would put that in the calculator. So I can just quit out of this, a second quit. A shortcut you have if you're going to be putting in fractions, you can hit alpha variables over here, x, and that's going to be our just a quick clear view. Clear entry, I think, is what they call it. That's what the CE is in the TI plus. CE, I think, is clear entry. All right, so our observation is going to be 6.78. Forgot the decimal there. It's kind of important. So 6.78. Then I'm going to take that minus the mean for all contestants, which was 6.16. And then I'm going to divide that by the standard deviation, which is what standardizes the whole thing, which is 0.23. Okay, so that's going to give me... Oh, I was supposed to subtract. Okay, so what's nice is you can actually go back up here and fix your error. I did it again. There we go. So we have a z-score for Kluft of basically 2.7, which means she was 2.7 standard deviations above the mean. Okay, so 1, 2, 2.7. There you go. All right, and then if we did the same thing for Sculietti, or whatever, how you pronounce her name, she was about 0.61, which would be about right there. So this tells us how impressive. So when we fit it to the model, when we divide it by the standard deviation, which is going to adjust for if we had a lot of spread or small spread, that's really the key to the whole thing. It's going to tell us how impressive was their score compared to everyone else when using a normal model. So she would get a z-score of 2.7, and Sculietti would get a z-score of 0.61 for the long jump. Now let's move on to the shot put. So we'll do the same thing. So observation minus the mean divided by the standard deviation. So I'm going to hit alpha x equals. And the observation, we'll do Kluft again, which was 14.77, minus the mean for shot put, which is 13.29. Then we're going to divide that by the standard deviation, which for the shot put was 1.24. Okay, which would be a z-score of about 1.2 for Kluft, or 1.19. Okay, so she had a decent one, kind of typical, but on the higher end. But Sculietti, when we do hers, is about 2.5. So overall, who had the most impressive one? Well, that would actually be Kluft's long jump score, because it was 2.7 standard deviations above the mean, or a z-score of 2.7, where Sculietti's her shot put throw was only 2.5 standard deviations above the mean. So overall, what we would have to do for that is add them together, which I think I did. Oh, that's nice. I did do that. All right, so we have 2.7 for Kluft in the long jump, 1.9. So her total z-scores, and again, we would do this for all 7 of the things that they competed in. I don't even know the word for it. Events, all 7 events, but we're just doing it for 2, so you see how it works. And then for Austria, we take hers. So add them up. So altogether, the one that had the highest z-scores. This is how we compare apples to oranges. Because long jump and shot put are two different things. But when we check and make sure that it's unable and symmetric, we can use z-scores, and the same z-score is going to have the same impressive value as a z-score for another distribution because it's being adjusted by the standard deviation for that one. For each individual event. So altogether, the more impressive athlete would be Carolina Klüft, at least for these two. When we add the other 5 events, we can see who the final winner is. But anyway, really cool stuff because stats comes in and saves the day and allows us to do some powerful things like comparing apples to oranges as long as we use z-scores. So the whole reason that this works, let me go ahead and go back to the formula, is because we're dividing by the standard deviation. Okay, so what that does is it takes things that had different units and it divides it by standard deviation to make the units now standard deviations. And that's when we say z-score, or the units we're using with the z-score is how many standard deviations. So this 2.51 means she was 2.51 standard deviations above the mean. Okay, so we're taking any event regardless of what it is, whether it's a shot put in meters or we're dealing with long jump in meters as well. Okay, but you notice the long jump had a standard deviation of 2.3, but shot put has a standard deviation of 1.24, which makes sense, right? The variation we have in how far someone can throw something is going to be a lot bigger than the standard deviation that we would have with long jump, right? Because the long jump scores are going to be much more consistent and tightly packed together. Okay, so anyway, the whole point of this, the reason it works is because we're dividing by the standard deviation. Well, when we divide by standard deviation, we're doing something called scaling. So we need to go over shifting and scaling. So shifting is whenever we move all the data points to the right or to the left, or I guess up and down, but it's really right and left. So let's say that we have the weights of these, I don't know, 150 men or whatever it was. We have their weights in kilograms. So we had some men that were around anywhere from 50 to 60, and then some over here we had a really big guy, an offensive lineman who's 170 kilos or whatever. But then over here we changed it, so now that we are graphing the kilograms that they are above their recommended weight. So let's say the average male has a recommended weight, it looks like would be about 100 or 80 kilograms or something. If I kind of subtracted from there, I don't know, we'll just go with 80 kilograms or 75 kilograms. I might be closer to, but whatever. All right, so notice that these two distributions are exactly the same. Do you notice that? It's the exact same histogram. That is so cool. Love that I can do that. It's the same histogram. The only thing that changed is we shifted all the data values by subtracting the recommended weight of 75 kilos or whatever. So this 50 is now a negative 24, meaning they're 24 kilos below weight, right? This 200 or 175 is now 100 because they're now positive 100 kilos overweight. Okay, so also notice the 5-number summary with our box plot or box and whisker plot and the outliers is exactly the same, right? That's yep, exactly the same. The number of men in each category was the same. The only thing that changed was this X scale by shifting it, by subtracting all of it by 75 pounds or whatever the difference was. Okay, actually, whoa, I could probably, if that's exactly the same, then it would be just the difference between those two, which is 74 pounds. Okay, so we subtracted 74 kilos, from each one of these. Okay, so what changed by the center? The mean, which let's say used to be, I don't know, say the mean used to be 80, now 80 minus 74, the mean is now 6 kilos overweight. Okay, so that's got subtracted by the 74. And the spread, whatever the standard deviation for this value is, now that standard deviation is going to be subtracted by 74 as well. Wait, no, it's exactly the same. I was totally wrong. Yeah, so the spread, the distance from here to here is going to be the same distance as it is over here. So when we shift something, the center would change. Any statistic like for the quartiles or the percentages or the range, or not the range, but anything that measures this a point, like a percentage or a point, is going to be shifted. Anything that measures spread like range, IQR, or standard deviation is going to remain unchanged. Because it's still the same width as it is in the range and the interquartile range or standard deviation. It's just all the values have been shifted. All right, the other thing is scaling. So let's say we want to convert it from kilograms to pounds. Now we're talking something I know. Wow, I guess he was actually 360 pounds. That's a big guy. Okay, anyway, so when we go from kilos to pounds, we're multiplying by a scale factor of 2.51 or something. I don't really remember. If it is 2.51, that's crazy. I don't know how I stored that information, but it's probably not. Hey, Google, what's the scale factor from kilograms to pounds? Anyway, so basic.
They say to convert kilograms to pounds, multiply the kilogram value by 2.2046226218. Do you want a little more context?
No, Google, that's enough. Anyway, so apparently it's that, not 2.51. That must be. I'm so embarrassed. Like I'm turning red. Okay, so moving on. Scaling, everything is going to be multiplied by whatever that scale factor is. Scaling is going to impact everything. Our measurements for like percentiles, our mean, our median, quartiles, and the ranges are also going to be stretched out. So we went from being crunched together with small units like kilograms to being stretched out with more precise units like pounds or Fahrenheit. Same thing with Fahrenheit and Celsius. Okay, so scaling would impact everything. Notice here, if we go from kilograms to pounds, it's the same distribution. If you notice that, it's the same like height, except everything just gets stretched out about from the mean. Okay, so anyway, yeah, there's our scale factor. So 2.205. Okay, I failed. Here's another way of also showing. So here's our summary, 5-number summary from kilograms to weight. Everything's being multiplied. Every metric is being multiplied by 2.205, our scale factor. Okay. Also notice the range is going to increase by the 2.25, including the overall range, the IQR, the standard deviation. Everything is going to change by that, and you can see it here. Every single statistic we could gather is going to be multiplied by 2.25 or 2.205. However, the difference is whenever we're when we're shifting, measurements of spread are not affected by shifting, only by scaling. Okay, we're not doing that one, or that one, or that one. Okay, example 1. 2 athletes compete in 2 events competition, shot put and long jump. Very similar to what we just did. Chris threw the shot put 63 feet, and Ryan threw it 66 feet. Chris jumped that high, and Ryan jumped that far. High, long, I don't know, it's late. Is Chris or Ryan the better athlete? So in order to be able to compare apples to oranges with 2 different events, we have to find z-scores. So just like we did before, take your observation minus your mean and divide it by your standard deviation. So let's find Chris's long jump. So Chris jumped that value. Okay, the mean for the long jump is in feet, so we would have to convert that. We're using units of feet. This could see if we just use metric, everything would be a lot easier. Okay, so we're gonna do 27.25. At least that was a nice fraction. Observation minus the mean for long jump, which was 26 feet, and then we're going to divide that by our standard deviation for long jump, which is a half a foot, 0.5. Yeah, careful, because we got to use feet for our units. So that's 2.5. So Chris, for the long jump, had a z-score of 2.5. Let me try this again. How about now? Okay, yeah, 2.5. And do the same thing for Ryan's for his long jump and do the shot put, then add them together. So I'm going to let you do that on your own. Let me do number 4 with you. So on number 4, it says specialty food company sells gourmet hams by mail order. The hams vary in size from 4.15 to 7.45 pounds with a mean weight of 6 pounds and standard deviation of 0.65. The quartiles are given, so this would be your first quartile, the median, and the third quartile. So that combined with the minimum and the maximum will give you your 5-number summary. Okay, they're just giving it to you in a weird form. So find the range in the IQR. So the range is going to be the max minus the min. So that's going to be 3.3. The inner quartile is going to be third quartile minus first quartile, which would give you that value there. Do you think the distribution in weights is symmetric or skewed? So when we compare the mean to the median, that will tell you whether or not it's skewed, because the mean is always going to be drawn towards the tail or towards the outliers, whatever direction it's skewed in. So if we have a mean of 6 and a median, the middle one here, was 6.2, that tells us that the distribution is slightly skewed to the left towards the lower values. So since it is skewed, it's probably not appropriate to use a bell curve to model this out. Okay, if the weights were re-expressed or scaled in ounces, from 1 pound is 16 ounces, so everything's being multiplied by some scale factor of 16. So this value here is being multiplied times 16. This value here for our maximum without an outlier or right fence is going to be times 16. The median's also times 16. You get the idea. The minimum is also times 16. So every metric is going to be changed. So take all of your stats in pounds. To change it to stats in ounces, you're going to multiply everything by 16. So 6 pounds is how many ounces times 16. The standard deviations times 16. Median, interquartile range, everything is multiplied by 16. So just plug that in your calculator and you're good to go. All right, but what about when we shift using, anyway, we're going to shift in this one. So the company ships these hams, the boxes and the packing material add 30 ounces. So we're shifting by adding 30 ounces to every data. Okay, what is the mean, standard deviation, median, IQR range of the weights of the boxes shipped in ounces? So take it from what we had in ounces, and now we're going to add 30 ounces to everything. But be careful, because the statistics that measure spread, such as standard deviation, interquartile, and range, are not going to be changed when we shift everything over. So the mean is going to be changing, but the standard deviation, interquartile, and range is going to shift with it. So it's not going to be impacted. So you're going to keep the same stats in ounces for these. You're not going to add 30 for the red ones here. You will add it to the mean and to the median, but not to the ones that measure spread. All right, if a customer made a special order of a 10-pound ham, which of the summary stats in part D might not change? So is not impacted by outliers if the data value were added to distribution. So when we have outliers, we don't use the mean and standard deviation. Instead, we use the median and the IQR. And the reason we use median and IQR is because they are not impacted by outliers. The median is the 50 percentile, right? It's the middle value where half people are higher and half people are lower, right? So we use it doesn't matter what's going on in the 99 or the 100th percentile. We want to know what's going on in the 50th percentile, which is not impacted by the outlier at the 0 or the 100 percentile. And the interquartile range is the middle 50% of values. It only measures the 25 to 75 percentile. What's going on at 0 or 100 percentile doesn't matter. It doesn't impact that. So those two are not changed, but the mean is going to be skewed. It's impacted towards the outlier. Same thing with standard deviation. It's going to be greatly increased by the presence of outliers. And ranges, we've already seen how badly those are impacted by outliers as well. That's why we don't use them. Only median and IQR when we have outliers. All right, so that's it. I hope you guys enjoyed it. We definitely got a lot more that I need to talk about when it comes to z-scores, but you kind of got the gist of the whole idea. So this will be probably one of the most important weeks that we have coming up, of course, ending this week with standard deviation and bell curves. So make sure you guys are caught up. And you have until the end of the month, so you got about 2 more weeks or so. It's till September 30th when we take the unit test in order to turn in all of your homework. So please get caught up. Whatever, if you've gotten behind, might need to make some adjustments to your schedule. You can just kind of do some reflections and see how you did. Overall, you guys did really well on the quiz. I'm really impressed. So keep it up and just make sure we're doing our homework. And if you need the extra help, the live office hours are always a good option. So anyway, I'm going to stop talking and I'll see you guys. Bye.